Okay, so we are going to finish up, our discussion with CIFAR10 and with deep learning. So you have an assignment due tonight, so it's basically just doing this. So make sure you submit that, or it'll close on Wednesday probably, right? All right, so this is homework 3, and it was just really working through this. I'll finish it up today, and I had done 2 videos, so this would be part 3 of that video series, just completing. It'll be under the title CIFAR10, and this is the part on deep learning, basically, so doing classification of it, and it'll help us to kind of complete that problem. So if you remember, we had covered, we talked about what CIFAR10 is, and then we talked about the libraries, and then we started to look at some examples of how to bring in CIFAR10 data into our code. So we also started to print out some lengths, some statistics, I guess, of the data set, and also to view some of the images. So all of this we have covered. Then after that, we introduced the topic of transforms, which is very handy in PyTorch, which allows us to do the scaling, and it allows us to convert data into tensors automatically. So that this is transforms over here. So we did 2 examples of transforms. One was for just creating regular pill or image data into tensors themselves. And then after that, we did normalization. So we went over that. So you can see that example here, the normalization example we covered in depth, and you can just reference back to video 1 or 2. All right, once we have the transforms and the, like normalization and converting to tensor defined, we basically just created a new way here of loading our data. So we created transformed CIFAR10 and transformed CIFAR10 val. And these were basically now getting the data from the datasets module, but also including in there the transforms where we composed tensor and normalization. So that we also completed previously. And then we just did some examples so that then finally, with all that together, we started to put together the data set that we need, building the data set for classification. Remember that this data set needs to have both training and testing data. So for every sample, we need to have a label. In this case, remember that CIFAR10 is basically images. We decided just to make this a binary classifier. So we only looked at 2 classes, airplane and bird. Okay. And then we have here a couple of list comprehensions where we take for image label and transform CIFAR10 if label in 0 or 2, right? So we only select those. And then we basically created tuples of images and labels using our label map, just to simplify the classification to 2 classes, 0 and 1. So once we have CIFAR2, and that's really pretty much where we left off. Okay, so that's pretty much where we left off. And now we are ready then to proceed to do the classification. So this is the standard part, which is what you needed to work on your assignment. Today, I'll pretty much go over it, and you can use this for your submission. So, at this point, the assignments have been pretty straightforward. I'm going to assign a new homework now that you will basically use this code, but it's going to be a different data set now. Okay, and it's going to be a data set that's available in a text file, and it's going to be pretty easy. This next assignment, which will be due a week from today, will be basically using this code, modifying it to classify the MNIST data set. Does that make sense? And the only difference is that the MNIST data set, now you will use all 10 classes, not just the 2 classes that we do here. Does that make sense? Pretty simple. MNIST is actually, there's a variation there because MNIST is only black and white. It's not RGB. It's not in color. Therefore, it will only have 1 channel instead of 3 channels. Okay, so that'll modify things a little bit for you, but that's part of the assignment. Okay, so just be aware of that. That's your next assignment, which I'll create the link for. All right, so now that we're here, we want to be able to do the training and the testing, right? If you look over here, we didn't do the testing yet. And for the training, we just kind of explored it a little bit. We have, we have to start to define things like, so we have our data ready, right? We have our data for training and testing ready to go. Now we need to do the training. We need to build model architecture. For now, what we're doing is we're taking images, which are usually 3 by 32 by 32, and we're just converting them into 1 by 30 by 72, right? So we're basically spaghettifying our images. So we also know that we have 2 classes, and this is basically how we build our models. So NN sequential, and then we have NN linear 3072 because that's the number of inputs. We have a hidden layer. This is a multi-layer perceptron of size 512. We have the 10, then the next layer, 512, to the number of outputs, which is 2. And just remember that at the end, we're adding NN softmax, which allows us to remember if we have 2 classes where the probabilities are being calculated, it'll basically, the softmax function, make sure that the probabilities or the values estimated by those neurons add up to 1. All right, that's the key aspect there. They add up to 1. All right, so that's basically the a definition, a simple multi-layer perceptron. And then here, if we want to test the model, for instance, since we have this model built already here, it hasn't been trained, but we can just grab an image, grab the image, the label, transform it. Remember, we learned how to transform our images by first using the -1, right? Remember that the -1 just takes the 3 dimensions here, 3, 32, and 32, and makes it into 3072, okay? So that's the trick there. And then the unsqueeze adds the 1. So that we end up 1 by 3072. This is important because very soon we're going to have to start thinking in batches, which means because if you're going to be using a GPU, you want to feed things in batches of, let's say, 64 or something like that. So you feed. So then this is consistent, 1 by 3072 versus 64 by 3072. So in any case, here we have a tensor, an image batch of 1 value. And now we're just going to feed that batch into the model, and it predicts the out, which is the prediction, basically. We print it out, and then, of course, this is a vector, right? The out is a vector of 2 things, right? And that's why we did the print. We had 2 values in there, but we have to pick one of the 2, right? That's what the model is doing, is predicting 2 outputs, and then we pick the highest, which is an indication of, well, I think this class has a higher probability than the other class. And we use the torch max function, which is very convenient. It returns the max value and index along the desired dimension in the tensor. So in this case, because we have 64, let's say, by 2, right? And so we're going to have, we're going to want these values along the 1 dimension, not the 0 dimension. Okay, and then we calculate the maxes, and then this would give us the max values and indices. It's important to remember that even though here it's only 1 vector, very soon we're also going to be predicting in batches of 64, etc. So we're going to account for that. Does that make sense? That's what we're going to do now. So now we are ready to lay this out, basically. So let's go ahead. We have that model, for instance. It's a very simple model. Now let's proceed to create. All right, so we're going to use basically, and we're going to create another little model. Let's say that. All right, so let's go over here. So this is basically from the previous code, right? Exactly as you had it from the last time. Now I'm just adding a little bit more. All right, so now I'm going to do same model, just a a few differences. We're going to change the softmax. There's another function instead of softmax called log softmax. And basically it helps with optimization when probabilities are very close to zero. Okay, so that's all it is. And so again, with deep learning, PyTorch, you have to experiment with all the different functions to see which one works best for you. So let's say a fully connected, so this is going to be a fully connected it's recording, right? Yeah. All right, so it's a fully connected neural net. Fully connected neural net. You know, we're going to assume input x vectors of 1 by 3072, or even better, or n by 3072, where n is the batch size. Okay, probably, you know, e.g. 64. That's usually like a common batch size, actually. Just feeding the GPU 64 at a time instead of 1 at a time, for instance. That actually makes a huge difference. But you can play, that could be 8, 32, you know, whatever you want. You usually, because the hardware GPUs will be memory, and they're sometimes multiples of 8. So again, the number of classes n out, that's going to be 2. So that's, you know, 2 classes, airplane and bird. Now we create model 2. Model 2, remember we call the module NN. From there we call sequential so that we can specify the architecture for this model. All right, and then we're going to build our architecture here, NN linear. We start at 3072. And then a mid layer, a hidden layer of 512. Then we've got, remember, the tangent h, which is our nonlinearity function, our activation function, basically. And then we have another linear here, 512, which is from 512 to the number of classes n out. Okay, and out. And then here, we just change it a little bit. It's just going to be the nn dot log softmax. And we apply it on the last dimension. So dimension 0, again, would be now the number of batches, right? So dimension 1 is the 37, the number of classes 2 in this case. All right, so I'm just going to add a comment here that this helps with optimization when the probabilities are close to 0. Okay, so it's just an optimization type of modification there. You can try it with just regular softmax. All right, now obviously we want to build not just neural networks. Yeah. You can't see this? How do I do that? How do I increase the font size? To what? Just 12? Yeah. Yes. 14? Big enough? How's that? All right, great. Yes, so yeah, that looks better. And yes, so we were saying that so far these are multi-layer perceptrons, right? They're not deep learning, they're just neural nets, right? But we want to build deep learning networks, right? More complex. So now we're going to go ahead and build a deep neural net here. And just, the great thing about this is that we can just change them, right? We select model 3, model 2, model 1. That's it, right? And they all work exactly the same because the inputs, the outputs are basically the same. What's in the middle, right, is what we change. So in this case, let's go ahead and do another one. Remember, this is going to be a deep neural net. So let's call it model 3. Let's go down here. Oops. All right, so let's call it here model 3. And then dot sequential and then nn dot linear. So now this is going to take a while because we're going to build a bigger deep neural net. So, we always start with the size of the input, x, 3072 in this case. Then now we start to build the layers in between, right? So I'm going to do 1024. That's 1. Right, then I'm going to add the activation function. In this case, again, we haven't tried anything fancy like ReLU or anything like that. We're just doing simple examples. So 10 H, right? Then we're going to do another one, and then linear 1024, comma 512. And then this one, of course, is going to have its own activation function. Remember how that works, right? So I'm going to do nn dot 10h. Then we have another one, nn dot linear. And this is going to be 512, comma 128. Notice that they're getting smaller and smaller, right? So this is that funneling effect that I was talking about. So it's like forcing the deep neural net to learn with less every iteration. And then now let's do, so that's 128. So nn dot 10 again, h, the activation function. Then we need another one, nn dot linear. And this one will be 128, comma 2. Okay, and finally, because this is, if it's 2, that means that's the last layer. That's the output layer, right? It's ending in the number of classes. So then now here we add the softmax, or in this case, the log softmax also we can try. And remember, as I said, this function, what it simply does is it makes sure that it will transform the values predicted in that last layer in such a way that when you add all of them, they add up to 1. Make sense? So they're going to add up to 1. So it's like saying I have 2 classes, I have a 30% chance of this one, 70% of that one. They add up to 1. Okay, so that's what the softmax function does. And later on, we can take a look at softmax independently, but you can convince yourself of that. And then it's going to be along dimension 1. So let me grab my pen here. So because we want to write this out, we want to write out that architecture. That's a really important thing that we want to understand a little bit better. All right, so let me save this so I don't lose it. Okay, so now let's go to the whiteboard. And if we take a look at that one, right, we want to see, okay, I wrote that code, but what does that architecture actually look like? Because I'm saying it's a deep neural net. So what we can say is basically this is the architecture, right? So there is the input. So this is the input. It's going to be the images, right? So remember that the images are technically a tensor that is 64 by 3072, right? That's what we're going to want it to be, or it could be 1 by 3072. It doesn't really matter. That's the great thing about this is the model doesn't care. Your tensor could be 64 or 32. The thing that matters is the 30 by 72, okay? But not, this is the batch size, batch n, that we need to specify in another way, but not in this network. So this network is only of size 3072. You guys see that? What that means is there are 3072 neurons in there, which represent the 3 by 32 by 32. Every image, we spaghettify it into the 3 RGB channels, and each one of 32 by 32. Remember, that gives us 3072. Is that clear? All right, great. Then according to that architecture, the last layer is 2. So I'm going to write it just about here. There are 2 neurons. This is the output. And that's the classes. But usually these values are going to be like 0.70, 0.80, something like that. That's what they're going to be like if we just do the network like this. That's why we need to run this through the softmax activation function. Do you guys see that? The softmax activation function will transform these values into what? 0.6 and 0.4, ensuring that they add up to 1. Do you see that, guys? All right, so don't forget that. I'll erase this, but that's what's happening there. All right, so that is the last layer. So in between, we want to figure out how many layers we have. So if we remember the code, we did 3072. The first linear layer was, if I go back to it, oops. All right, so this is the one we did. So we have the first layer is 3072 by, and then 1024, then 1024 to 512, then 512 to 128, and then 128 finally to 2. So these are the layers, right? And now we want to visualize them in our graph. So we can go back to the whiteboard, and now we know the next layer is 1024. You see that? So this one is 1024. It's a fully connected layer. What that means is there are 1024 neurons in here, and every single one of these neurons is connected to the previous 3072 neurons. Think about how many parameters that's going to be, because this is a weight matrix. You guys see that? It's a weight matrix that's going to be 3072 by 1024. Think about that. Just there, you have a matrix that is 3072 by 1024, because this one needs to be connected to every single neuron here. That's one neuron connected to 1,024. Do you guys see that? That's that first layer. Well, actually, yeah, that's that first layer right there, that first row of weights, just weights. And then you do the same for all of these. The last one, the last neuron 3072 needs to be connected to all 1,024 of the next one. So imagine, that's why it gets so crazy with deep learning, because you have all those parameters have to be learned. You guys see that? You don't have them right now. They're just random data, but these matrices, these need to be matrix operations to be done efficiently. Okay. Then the next one is from 1,024 to 512. So yet another layer, right? And so this one has 512 neurons and it's fully connected. So that's another, right? Another matrix, right? That another weight matrix that needs to be created. Then from 512, we have another layer 128. And then finally, the 128 layer is connected to the layer that has two neurons, the output layer. You guys see that? Makes sense? All right, so this is, when you only have one hidden layer, this is a neural net. But when you have two, remember, this is X, usually, that's Y. Y hat, usually the predicted Y. And then we have hidden layers, H1, H2, H3. This is a deep neural network of 3 hidden layers. Is this clear, guys, for everyone? Okay, great. So now if I tell you, do a 4 hidden layer, you should be able to figure it out and build it. That's why it's called architecture, because you build this architecture. Questions? All right, great. So let's continue then. We're going to go back to the code. We're going to go back to our code. Switch over. All right, so now we have our deep neural net. Now we need to define, remember, some of the parameters, right? So we want to define the loss function maybe that we want to use. Guys, any questions? All right, so we're going to define, we have the models basically. Now we need to define the loss function and various other things. However, before we do that, there's something really handy. PyTorch is all about helping you. And I've always been where I like to do everything from scratch, but we're getting to a point where there's so much data that using all the tools is very helpful. Because nowadays there's so much data that even dealing with the data, you need something to help you with that. How do you how do you get the batches? How do you shuffle the data randomly? Instead of doing all that processing manually, there are some tools to help you with that. So let's go ahead and try from Torch. One of the many examples of this. Let's use the data loader. So the data loader allows you to define batches, which, remember, our batches are going to be of size 64, and we're also going to do shuffling. All right, shuffling just means randomize the data. Remember, in theory, whenever we basically load the same data, several times, right, based on the number of epochs. And wouldn't it be better if whenever we load the data, it's actually shuffled every iteration? That's actually good, right? That means, it's like I grab a whole bunch of tennis balls, right? And I do this, and then I grab one, and then I do this, and I grab one, right? So I'm shuffling them, so I'm randomly kind of trying to train the model many times. All right, and this is just very easy. We create an object called train loader, for instance. Okay, and from Torch, we call utilities, utils, and then from there, .data, and then we're going to call the data loader. Right, so we call the data loader. Remember that our data is now in CIFAR, right? So CIFAR2 and CIFAR2 val are the two that have the transforms and everything, but we spend all that time in the last lecture. So now we just have to tell it that we want to use CIFAR10, so this is the train data. And we also want to specify the batch size. This is handy because whenever we use data loader will no longer just give us one image. It will always give us a tensor of 64 images. Okay, and that makes it very handy. So it's going to be batch size equal, we assign to it the size. So in this case, we're going to assign it 64. Okay, and then we also tell it that not only are the batches of size 64, but you know what? Shuffle them. That's it. You don't have to do it. It does it for you. So that's kind of handy because this is already a tensor. And so remember, that's the key here. You know, remembering that everything's a tensor and you want to do things that way. Now, I have several models here, model 1, model 2, model 3. I'm just going to grab the deep neural net and I'm going to assign. So I like the old approach of having 4 main functions that you always call upon: loss FN and model FN, right? And I'm going to follow that same approach. So I'm going to go ahead here and just, you know, kind of define my functions, right? So this, you know, I usually call this area calling the main functions. So I mean, it's just, I like to have like a template that I always follow. So call main functions. And so in this area, I can define the functions that I'm going to be using later on in the code. So I need model FN and also loss FN. So that way, I write all my code in terms of model FN, loss FN, but if I need to make a little change here and there, I just make the change in this section. So here, model FN, I'm just going to use model 3. Okay, so I'm going to use model 3, which one's model 3? The deep neural net that we just defined with the 3 hidden layers. Okay. And then loss FN is going to be some functions. So eventually we will arrive at the point of cross entropy, which is probably what you have seen if you've taken a machine learning class before. It's always classification, always, you know, cross entropy. You probably learned that so before, but in this case, we're just trying out different functions. So in this case, we're going to try another function called, it's called the negative log likelihood, which is similar to cross entropy. If you want to learn more about that function, you can read about it in your book, the PyTorch book that we're using in this class on page 180. So I strongly recommend that, obviously, hopefully you're following along with the book and just read about it. You know, usually the only function I spend time on is cross entropy, but this is just a variant of it. So it's called a loss NL, or negative log likelihood. But you can read more about it on page 180 of the book. So in this case, we're just going to assign it to loss FN. So again, we go to NN, the NN module dot, and then NLL loss. Okay, we also want to specify a few other parameters like the learning rate. So the learning rate. And remember, we're using, you know, something like 0.001, right? So we're just going to write this in exponential. 1e minus 2, let's say. Okay. So once we have the learning rate defined, the last thing we need is the optimizer, right? So we need to define our optimizer. So in this case, we can use the stochastic gradient descent that we've used before. So I'm going to do opt from the optim module, right? Remember that we called at the top. I'm going to call SGD, which stands for stochastic gradient descent. And that's basically the function that, you know, goes along and looks for the weights the one that's based on calculus, basically, and the derivatives. So now what do we need to provide to this function? Well, this function is going to use the learning rate. So LR, and that's just going to be the learning rate we just specified. And also we want to specify in here the thing that we're learning, right? With stochastic gradient descent, which is going to be the weights and the biases. And the weights and the biases, remember, we've called parameters in Torch, right? And they're in the model. So if we want to reference them now, we can simply do model, this model up here, right? Model fn dot parameters. And then that way in the computational graph, these things are linked now. And so basically the optimization will try to learn those values as it goes forward and backwards in the approach. All right, and then once we have that specified, we can proceed to the main loop. Remember, now that we have called basically we've linked everything, right? So this is the point where we kind of link everything in the computational graph, if you will. And now we can proceed to the main loop. And let's say the main loop for training. So this is our main loop for training. So we're going to have here, let's say for epoch in range n epochs. Okay, where we define n epochs, of course, let's say n epochs equal 100. So we don't need that much for this model. Other models may need a lot more epochs. So for epoch in range, n epochs, remember this is just us repeating the same process. So reading the entire data set and training with it. Okay, and then remember we have the validation for the testing later. So now that we have this, we can simply, we're going to repeat this process 100 times. And now we proceed to the second loop. So 1, 2, 3, 4. This for loop, remember, is the one that actually scoops up the batches. Okay, now you can do this from scratch, but in this case, we're not doing it from scratch. We're just using the data loader. So I'm going to say here, for images, comma, labels, because remember, we are now grabbing 64 of each. Okay, instead of grabbing one image and one label, this will grab 64 images and their corresponding 64 labels, and they're going to be, aligned by index, right? In the tensor. So it should be. So here we have for images, labels in, and this is where we use train loader, which is the object that we've defined. So remember, every time now we're grabbing a batch of 64, and by the way, the images are shuffled, right? The images and the labels are shuffled together, so they're going to match. It's not like we're losing the order, they're just shuffled, okay? All right, so in this case, we can say here, for instance, images should be, oops, let me grab a comment here, and we can say images. That's a tensor now of size 64 by 3 by 32 by 32. You guys see that? We still need to spaghettify it, right? To be 64 by 3072, but we've got 64 now of these. Make sense? Okay, great. And so we also have the 64 corresponding labels assigned in this. I suggest that when you do this on your own, print out the dimensions of both of these tensors to get a better feel for what's going on. Okay, that's certainly a recommendation. But just keep in mind, labels is also 64 by the number, by 64, a vector of 64, which contains the labels that correspond to these images, all shuffled, but all in order. All right, so now I have images and labels, and now I can proceed to train the model. So before I train them, so to train the model, remember, what we do is we take the images, run them through the model, and the model predicts. Then what do? That prediction is new labels, right? We predicted these labels for this. We compare those labels to the real labels, right, through the loss function, and then we decide, okay, how well did it do? Based on how well it did and the stochastic gradient descent algorithm, we adjust the weights. That's it. Does that make sense, guys? It's a very key concept, but that's basically what happens. So here, 1, 2, 3, 4. Okay, so the first thing we want to do is we want to figure out the batch size. Now, the batch size is 64, so we could literally just hard code it. However, what if you decided later that you wanted batches of 128 or 32 or 8, because you just want to experiment, right? So you probably want to automatically get the batch size instead of hard coding it. That's always recommended, that you don't leave anything hard coded. So just do batch size. And then from images, right, we just need to grab the first shape, because the first shape is the size of the batch, 64. Right, so we're going to say batch size 0. Okay, so we have the batch size, images shape 0. Now we're going to proceed and do the prediction. So we're going to call this outputs. And in outputs, we're going to call the model FN. And we're going to make a prediction. Okay, so this prediction requires the use of the batch images, but because the batch is still 64 by 3 by 32 by 32, it needs to be adjusted, right? And so the way that we're going to do this is we're going to use a view, right? That example that we did before of the views. So IMG's view, and then now we need to be specific. We need to spaghettify it, but before we spaghettify it because it was only 3 by 32 by 32, and then on squeeze to add that first one, right? So that we ended up with 1 by 3072. We no longer need to unsqueeze because we already have the 64 in there. It's already unsqueezed, right? So all we need to do is keep the 64 dimension, but then the other ones, the 30 by 32 by 32, needs to be made into 3072. You guys see that? And it's pretty easy. All you have to do is, this is made very easy with this. Just say 64, or even better, batch size, because that tells PyTorch. PyTorch will understand the order, and it'll say, okay, leave the first 64 as is, but then do -1 for the rest. Got it? That's the trick. And that trick is used in TensorFlow, and it's used in NumPy. It's actually, NumPy invented it, and then it was them that kind of copied that approach. Do you guys see that? What's that? The batch size is not right? Oh, yeah. All right, so there you go. So is that concept clear, guys? That's a very important thing when dealing with tensors. You'll do a lot of this. If you do deep learning, this is a thing that you will do constantly. These are the little tricks that pay off a lot in terms of coding. Just doing that little trick takes care of a lot. So anyway, so we do the images view, batch size, and then -1. And this will basically output, if you will, that view will now give you a tensor, which is 64 I3072. 3072. You see that? Huh? Yeah, so what I said is, remember that your tensor looks like this, right? Then we do the images view. Remember, this images view, if you don't remember, we saw this in the previous videos, right? We spent some time on it somewhere up here. There, right, on how it worked, right? So make sure you go back to that. But the idea is that we need to make, and really it goes back to this. If I do share a screen, it goes back to the fact that the input expects vectors of 3072. Okay, so we need to spaghettify that, but it needs to be able to take batches of 64 or whatever. And PyTorch is made to do that. It can take any number of inputs as long as you have defined this dimension. And so that's what we're doing here. We're grabbing this images, right? So we extract 64 images and 64 labels. We have a batch that looks like this one. And now we're going to use view to basically convert it into 64 by 3072. Because we fix the 64 by just saying batch size here, which is 64, and then the rest -1. So it'll make the other 3 dimensions into 1. Got it? All right, great. So now that we have this part, we have the outputs predicted. Now we need to compare, how well are these outputs compared to the real labels, right? And so to do that, we calculate loss, which is basically loss Fn, because remember, these functions are already defined by PyTorch. They take 2 inputs usually, the predicted labels and the real labels. Compares them, and then it's going to do the calculation, okay, via stochastic gradient descent. So loss Fn, then as you might imagine, will take outputs. You see that? The tensor of outputs, and it also has a tensor of labels here. You see that, guys? Make sense? Okay, so we've got this loss functions. It's like saying, I predicted these 3 are birds. That's the prediction, but only 2 out of 3 are birds, right? So it's going to make that comparison. And then stochastic gradient descent uses this information to calculate the weights, right? It needs to propagate because it now predicted the values. Now it kind of needs to propagate back and adjust the weights accordingly. And that's where we go in here, remember, and we do 3 things, right? This is purely a mechanical thing. Optimizer. This is something that TensorFlow doesn't have, for instance. TensorFlow, but here, it's just they wanted a way to be able to see cumulative values. But we, unfortunately, then we have to kind of like erase it. So you say basically here, optimizer 0 grad. It's kind of like zeroing out the gradient. All right, so it doesn't accumulate the old values. It only uses the current values. So that one, it's kind of like you just have to put it in there. And then after that, you tell it, okay, now go backwards. So loss backward. So all these mechanical things you do in PyTorch, which you don't have to do in TensorFlow. And then finally, it's going to take a step. So you do optimizer dot step. And that basically is the process. You can think of these 3 lines of code as, okay, now calculate the weights. Does that make sense, guys? So that's the step. So usually in PyTorch, in TensorFlow, it's only this step. But here you have these 3. And so now that's it. You've adjusted at this point in this iteration the weights. And now you do it again, right? It's because it's a for loop. So now you're going to grab another batch of images and labels, run it through the model, get outputs, compare it to those labels, take that loss, which is already associated in the graph, right? And then you take another step and another step. And every time you're doing that, you're adjusting the weights. And hopefully it's learning more and more and more, learning the tendency towards the real set of weights. Got it? All right, now that we do this, we usually, it's standard practice to kind of view what's going on. So for every epoch, let's say 1, 2, 3, 4. So for every epoch, we're going to print out some values. In this case, we can print out the epoch percentage D. We're going to use format strings here. The loss percentage F. And then we're just going to provide the values, which are going to be, in this case, epoch is just a variable epoch. And the loss value, as it is at the end of that iteration. And we're just going to run it through a float conversion. All right, so we can look at the loss. And remember, the intuition with looking at the loss is we want the loss to do what? Go down, right? Usually we want to see that loss, which means intuitively, if we go back to linear regression, it's like we're minimizing the number of errors. So intuitively, that's the same idea here. We're minimizing the error. Okay, so now that I have this defined, I can go ahead and run the training. So hopefully this will run. So let's go ahead and just run it here. Does it run for you guys? Yeah. As you can see, it's slower now because 64 images, right, of 64 by 30 by 72. This is now real data. Okay, that you could be doing a project like this, you know, and so at this point, certainly using a GPU starts to become a good idea. You see that? And so, because it's taking a while actually. So this is, you know, kind of, we're limited here by Scholar and its resources. I think the instances that, obviously the instance I'm using is CPU based. But you can see the loss there. I don't know if anyone is running this on their laptop. Is it faster on your laptops? Huh? Significantly faster, yeah. 60 seconds, the whole thing? Okay, great. Yeah, you can see I'm only at epoch 1 of 100. So certainly, you know, our resource is Scholar. I don't know that we have the GPU instances easily available in Scholar, or we have to request them. But you know, as you heard, using your laptops might be, you know, a good idea. All right, so it's currently at Epoch 2, or otherwise you'll have to wait. This will probably take 30 minutes to finish, it seems. But keep in mind, it's a good sized data set, right? So we're talking about 60,000 samples here. That's why each epoch, remember, each epoch is grabbing 60,000 images. I mean, it grabs batches of 64, but there's a total of 60,000 images. So it takes 64, then another 64 until it completes 60,000 of these. It does all. It's also a deep neural net with a lot of layers. You saw how many weights we had in there. So it's significant. Okay. Obviously, this is not big data, though. I should stress this is not at all big data. Big data would be on the order of millions of records, right? And here we only have 60,000. But you know, good thing is the model seems to be learning. The loss is going down, so that's definitely a good sign. Okay, guys? Any questions about this? All right, let's just do the last part then, which is the testing part, and then we'll be done with this program. So obviously, I'm going to kill this because it's taking too long. All right, go back to the code. And then you'll just have to run this. You know, remember, you still have to submit this assignment. So this is the training section. And then after it trains, the model is basically done, right? And so now you want to do the testing. So you move, let's say, to this section. We're going to do the, you know, basically use the model, right, to predict. So now this is testing. So what do we need? We want to use a new loader. So let's call it val loader. All right, and again, we call torch dot utils data loader. And this one is going to be based on CIFAR10 underscore val. Remember, that's the other one that we created. This is the validation data. It's the model has never seen these images, right, in the training. So CIFAR10 underscore val, comma, batch size. Again, we want to specify batches of 64, which again, that would become very useful if we were using a GPU. Batch size 64. And then, of course, we want to shuffle. So we're going to set, or does it matter that we shuffle here in the testing? No, right? Because it's only testing. It's not about training the model. So actually, we can set that to false. All right. And then now in the next lecture that we're going to do on next week, I'm going to now introduce how to measure performance. All right. Today, I'm only going to show accuracy, but next lecture, we are now at the point where we need the performance metrics because you guys will start doing these assignments now of classification. Remember, I already gave you the assignment for next week, which is this code, but with the MNIST data set. Should be an easy transition. So we've got the val loader. We're going to need a couple of variables, the number of correct samples versus the number of total samples so that we can do the calculation of accuracy. And what that means is simply, you know, we have out of 300 total samples, 250 were correctly classified. So 250 divided by 300 gives us accuracy. And that's a very simple calculation. The other ones will be a little bit more complex. So now we have the val loader, we have our variables. So now let's just say with torch dot no grad, which basically means don't learn with this because this is testing. So we're not training the model. Okay. This is, and so basically we're telling the gradient, you know, the graph, basically the computational graph, hey, don't learn the gradients. Okay, so that's how torch is one of the things that peculiar things about Torch, but it does things like this. So with torch.nograd, and then we repeat the process. So 1, 2, 3, 4. We have our for loop. Here, we don't need epochs either because we're not training, we're just testing. We just want to see how it does on the held out data set of like 10,000 samples, I think it's. So that's going to be for IMG's labels. Again, this time we grab 64 images, corresponding 64 labels from val loader. From val loader. 1, 2, 3, 4. Again, we calculate the batch size. We did before, which is just going to be IMG's tensor shape, and we say that we want the first dimension, right? The batch 64. So we've got the batch size, and then now we're going to predict. So we're going to do outputs. And we run this through model FN. We run this through model FN. We have to, once again, use a view. So we're going to take IMG's view, and we say 64, comma, -1. So that's going to be batch size, comma, -1. Right? Remember, this just makes the tensor be 64 by 3072. Once we have the output, we've really predicted, right? We've predicted what we want, and now we're going to, we have a tensor of outputs. We just have to select the label, right? The label is going to be, for every one, we have the output vector, right? So we have 2 neurons in each one. So we have to predict the highest one. Make sense? Remember that it looks like this, right? If we go back to this one, we basically have 64 by 2 in there, in that tensor. And now for each one of the 64, we need to pick which one of these is the highest. And so to do that, we are going to use the torch.max function. So remember that the definition of torch.max is it gives you the value and the index, okay? Value and index. So we don't want the value, so we can just do like an underscore, and that just basically goes to, but we do care about the index, which is the label, right? The predicted value, 0 or 1. So then we do keep that one. So we use torch.max of outputs, and we need to specify the dimension. Remember, this is 64 by 2, so we need not the 0 dimension, but the 1 dimension. Take it out of the ones and not the zeros. So this is going to be 1. Got it? So now I have my 64 by 1 basically result, and I can just calculate the value. So the first thing I need is I'm going to calculate the cumulative number of total samples that I look. So first time is 64, then it's 64 times 2, then 64 times 3, right? I need to accumulate all those totals. So that's pretty simple. We have a running total basically. All right, so running total is going to be from labels, let's say. This could be also from images. Shape. Zero. We could have just done 64, 64, but what if you change the batch size, right? So with this one, it's always going to be dependent on the batch size, but cumulatively, you're calculating how many is the running total you have. That's the total, and now we just need, out of the ones predicted, how many match the real ones. You guys see that? All right, and to do that, actually, this is a trick that is very common in NumPy, TensorFlow, PyTorch. We just, another running total, correct we're gonna int this, right? So that an integer. And basically all we have to do is in here, we're gonna compare out of, let's imagine we have a vector of predicted, right? That's one vector. And then we have a vector of labels. Do you see that? So all we do, this is a trick you can do in NumPy, just do like that. That operation will return in a new vector of only the ones that match. You guys see that? So like if I had, you know, true, false, false, true, and then I have true, false, true, true, right? So this one matches, this one matches, this one does not match, this one matches. So then this was 4, but now the output of this is 3. Only the ones that match. Do you guys see that? Okay, and so that's what that trick does. That's from NumPy. And so once we have that, then we just do dot sum. And sum just basically sums it. So 3, so out of 64, 3, out of another 64, 50, out of another 64, 17, whatever, and it's keeping that running total. You guys see that? That's it. And then you calculate the accuracy. So now we can proceed to do print. And then we just print out the result, and that's it. So we do accuracy. Let's do another format string here. This is a division. And then we can just do comma. And then just divide correct divided by total. And that's it. That's it. And that's a simple accuracy. Later on, we're actually usually, I think in the future, we're going to use functions for all of these, even though accuracy can be done like this, we're probably just going to use the functions of these metrics. So it's even easier for us to calculate. But for now, I've done it this way. I'll introduce those topics. The metrics that are coming are accuracy, precision, recall, F measure, and the confusion matrix, right? So we need to develop those functions. They can be done in sklearn or PyTorch or, you know, many approaches. And that's it. So I've concluded the code. Now you have to run the rest. Make sure you run the rest of this on your computer. You need to get results and then submit this as part of your homework. The next homework is, so I'll do that. So I'll stop the video now. Let me do that. But before I forget, we have 6 minutes. So I'm going to stop the video now.